So I am going to talk about minimum spanning trees, or MSTs. So given some undirected graph with weighted edges, the minimum spanning tree, simply put, is just a set of edges that most easily or most cost effectively connects all the nodes in the graphs. So in this graph, obviously there are a bunch of redundant edges connecting all of these nodes. So the idea with the minimum spanning tree is just to find the lowest total edge weight that we can use to make sure that all of the nodes have some path to all of the other nodes. So in this example here, right, we could still have a connected graph if instead of using this 5-weighted edge, we use the 6-weighted edge. But in that case, our total edge weight would increase by 1, which is why we use the 5-weighted edge instead of the 6-weighted edge. You can just sort of think of this as an example with like a telephone company who wants to lay down wire, right? If all of these nodes are houses and all of the edges are potential places that that company could lay telephone wire, and the weights are the costs of laying the wire in that place, then the minimum spanning tree is just the cheapest way for them to lay wire that connects all of the houses. So that's all a minimum spanning tree is. And there are two good algorithms to find the minimum spanning tree of a graph easily. The first one is Prim's algorithm, and the second one is Kruskall's algorithm. So I copied that graph a couple more times here, and I'll go through Prim's algorithm once and Kruskall's algorithm once, just to show you how they work and what they look like. So Prim's algorithm is a pretty simple routine. So we just pick a random node to start on, and that's how we start Prim's algorithm. And then we just have a minimum priority queue, right? So this is referred to as the fringe sometimes. And basically, it's just all the edges that are incident on the solution that we already have. So the solution that we start off with is just the node that we pick randomly, right? And the edges that are incident to that node, in this case, are 3, 1, 6, and 2. Those are the weights of those edges. So 3, 1, 6, and 2 get dropped into this minimum priority queue. And the next step is just to take the smallest thing out of that priority queue. So it's the 1 in this case. And we just add that edge into the solution and whatever node it was connected to. So now, because our solution has grown, so does our fringe, right? Because we also have some new edges that are incident on our solution. We have the 7, the 8, the 4, and the 9. So let's add those in. Okay, and now we just repeat. So we take the next smallest item out of the priority queue, which is the 2. Add that in. And now we have a 5-weighted edge that gets added into our fringe. So then the next smallest item out of the fringe is the 3. We add that in. The only new edge that's incident here is the 4, right? So now we have 2 items that are tied for the smallest. Doesn't matter which we pick. We'll just do the 4 that we added in first. And you can probably already see that there are 2 equally valid solutions we could have ended up with. There's no rule that there has to only be one minimum spanning tree, but as long as it has the minimum total edge weight, it's a valid solution. So we don't have any new edges to add in there. The next smallest element is a 4, but since it wouldn't connect us to any new nodes, it's redundant, so we'll skip over that one. And the next one is a 5, which connects us to our last missing node. And now we're done. So we have the minimum spanning tree for that graph, which matches what we had in the beginning there. We found that using Prim's algorithm. And then the other approach is Kruskall's algorithm, which is less about starting at one node and more about you have all the nodes in the graph and you just want to start connecting them to each other in the easiest way possible. So you can think of these as 6 individually connected components. They're trivial at first, but as we start to connect them, the goal is to just connect any of the connected components that are separate in the easiest or cheapest way possible. So we look at just all of the edges on the graph that connect separate connected components. So right now, that's all of the edges in the graph. The smallest edge in the graph is this 1-weighted edge. So we're just going to add that right into the solution because we know that will be there since it's the smallest edge that can connect these two components. So now these two components become one component, and instead of having 6 like we started with, we only have 5. So the next smallest edge to connect two unconnected components is this 2. So we'll add that into the solution. And now we have one fewer connected component. We have 1, 2, 3, 4. So the next smallest thing we have is this 3, which connects these two components. And then we have 2 4s, equally valid. Let's pick this one just to show that we can do that if we want to. So now we have just 2 connected components. And again, we see that we have a 4 here, which is the next smallest edge, but it doesn't connect us to the other component. It just adds a redundant connection here. So we'll skip over that and move on to the 5, which is the next smallest edge. And once we connect that, we can see that everything's connected, and we have the minimum spanning tree once again. Ordinarily, crucicles and prims give you the same solution. I chose to pick this separate 4 just to demonstrate that's possible. But the point is, either will give you an equally valid minimum spanning tree. You can usually just use whichever one you prefer. So that's minimum spanning trees.